Hi, this is the first of two videos keyed to a section in Young and Freedman's University of Physics which is on the mathematical description of a wave. I've divided it into two different videos. So we're going to talk in this video about kind of deriving the wave function. This is pretty important stuff. Even though this is in a chapter on mechanical waves, this wave function we're going to develop, wave equation in this and the next video, basically work for electromagnetic waves, for longitudinal waves, although we're going to talk about transverse waves in this video, up and down waves. So this is pretty big impact stuff. Well, let's begin. Deriving wave functions. You might remember from an earlier chapter, simple harmonic motion. That's like, for example, a spring going boing, 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 boing. Simple harmonic motion. There we found that you could describe any x or negative x, in a simple harmonic motion by x equals the amplitude, which is the maximum displacement from its resting spot, times the cosine of omega t, where omega is something called the angular frequency. You probably know frequency, cycles per second, or hertz, somewhat commonly. Angular frequency is radians per second. So if we think of frequency in terms of the number of circles per second, so to speak, and we think of a circle as being 2 pi radians, then basically 2 pi times the frequency gives us angular frequency. So since omega equals 2 pi f, another way of writing this same equation is x equals amplitude times cosine of 2 pi frequency times the time. Okay, that's all review from a previous chapter. Now, by the way, you might remember from that previous chapter there was also a phi in this equation. So it was cosine parentheses omega t plus phi parentheses. We're ignoring that, or they're ignoring that in this section, because that would just make things complicated. The phi, if you remember, was what if it starts out of phase? In other words, what if your spring doesn't start at the resting point to where its starting point is somewhere else? And so that's what the phi is for. But we're going to ignore the phi for this video. Okay, so let's see if we can come up with if we can apply this equation for simple harmonic motion in a way that can help us come up with an equation for a transverse wave. Remember, a transverse wave is an up and down wave, like if you took a rope and went, and it went like that in a sine kind of wave. Let's see if we can come up for an equation, a function that would express the movement of the up and down. So to start things simple, they start with, okay, let's see if we can come up with an equation for x equals 0. So let's say I go, and the rope goes in a sine wave and keeps undulating. Can I come up with an equation for what the thing does up and down at x equals 0 at the starting point? Well, I can. It's very easy. Basically, it's the equation for simple harmonic motion that we just reviewed. And so, if I'm looking for a function of y is up and down usually by convention, at x equals 0 for any time, then it's basically just the old-fashioned simple harmonic motion equation. That was easy. Okay, but what about beyond x equals 0? What if we're trying to look at the up and down? We want an equation for an up and down spot on the rope that isn't at x equals 0. Well, let's think about it for a second. So the wave is going to move at a constant velocity. You might remember from that earlier chapter that the velocity of a wave depends entirely on the medium. Doesn't matter how hard you do it. The medium, like the rope or whatever, the wire, is or the spring is going to require is what's going to determine the velocity. And so we can basically see how far out of sync any x is from x equals 0. By basically taking into account the amount of time it takes for the boing, to reach that spot. So for any future amount of time. We know that velocity equals distance divided by time, right? So we kind of rearrange that equation, and we get the time equals the distance divided by the velocity. So the time to get from x equals 0 to some other point x is going to be that distance x divided by the velocity of the wave. That tells me, in a sense, how far out of phase, how far off from x equals 0 that other x is. Now, so basically, if I think of t in this next equation down here, if I think of this t as any subsequent time, it could refer to, because it's going to go up and down out here. So time doesn't stop when the loop first gets there. It keeps going. And so any time t in the future is basically the total time minus the time it took to get from x equals 0 to the point I'm trying to get an equation for. I hope that was vaguely clear. Basically, I can substitute that back into the original formula. I can now say generally, not just for x equals 0, but y going up and down, an equation for the up and down of any point x, positive x, is going to be the amplitude times the cosine of omega t, but here t is the total t minus the amount of t it took for the wave to get from the starting point to there. That's how far out of phase it is, so to speak, with the starting point. Okay? So there you have, if you don't understand, just memorize the equations. Now, this can be rearranged, this formula we have here. So, for example, physicists like to abbreviate things. They come up with this constant k that is basically 2 pi divided by lambda. Lambda is the wavelength. Remember, the wavelength is the distance between crest to crest or trough to trough, or from any one point on this wave to the equivalent point on the next wave. That's the wavelength. And so if you take 2 pi and divide it by the wavelength, physicists have come up with a constant k to describe this. Don't worry about why they did it. It just becomes useful in simplifying equations. So, for example, if I take this into account, I can play with this and come up with this. That's a lot simpler. I mean, look, this has brackets and parentheses. I can do this in just parentheses. So here, this is an equivalent equation. Basically says y for x and t is going to equal the amplitude times the cosine of kx minus omega t, where this is what k is, and x is again the distance out from the starting point, and so forth. Okay, so there's 2 different forms of the equation that you can use when a problem gives you different variables. There are more. So here's another equivalent equation. Again, just substituting in stuff. What is capital T is the period, which is 1 over the frequency. There's the lambda. That's the wavelength. So again, you can look at the book or a book, and it'll show you how to do it. But it's just basically algebra, rearranging things, substituting in stuff. So this equation works when you have, say, the wavelength and the period instead of, say, the frequency. Okay, well, that's just some equations to have on hand to solve various problems that are given you, that give you different data, different information that you want to plug in. Okay, what about different x's at t equals 0? So we did the function as a function of time for various x's. What about at t equals 0? If I took a snapshot of this wave at t equals 0, can I come up with an equation for that? Well, sure I can. All I have to do is substitute in 0 for the t up here, and this second term will disappear. And so again, we'll have different equivalent forms. Here's the form that basically substitutes the t equals 0 here. If I go back to the previous page and I substitute in t equals 0 here, then it falls out, and I'm just left with cosine of kx. Which is this form here. So here's an equation when t equals 0. It basically gives me a snapshot of what the wave looked like when I click the stopwatch. Okay, now last slide in this video. You can also do everything that we've just done for a negative direction. So everything that we've just done, we've done for a positive direction, and it ended up being a cosine of kx minus omega t. You can also calculate it for the negative direction of a wave, and then it basically, instead of it being minus omega t, it becomes plus omega t. This quantity right here kx plus or minus omega t is sometimes called the phase. And we can talk about the speed of the wave. Another way to talk about the speed of the wave is, since it's going to be constant, this part here is going to equal a constant. And so if I take the derivative, let's say I have kx minus omega t equals a constant. So if I take the derivative of both sides of this equation, so let's say that I take the minus omega t and I put it on this side of the equation. So then I have kx equals minus omega t plus a constant. Let's say I take the derivative of both sides. Well, I'm going to end up with k dx dt on the one side, and then I'm going to end up with omega on the other side, because the derivative of a constant is 0, and the t goes away. If you don't know calculus, don't worry about it. Basically, it comes out this way, that the instantaneous rate of change of the distance in relation to time is going to equal omega divided by k. And so basically this is another velocity. This is called the phase speed. And so the phase speed, the speed of the wave, another formula that you can have in your hopper is the phase speed equals omega divided by k. Well, this was a bit of a complicated one, but I hope that it shed some light on the section.